Good afternoon, everyone. As stated, I'm Warrant Officer Class 2 Kyle Roberts, and I'm here with my colleagues Corporal Killion, McKenzie and Lance Corporal Nathan Parsley. We're from 42 Engineer Regiment based up in Cambridgeshire. We're part of the capability development team that we've got up there that consists of between 6 and 10 people, depending who's in work at the time. We've been invited today to discuss our recent innovation project. We've been working for the last couple of years now to try and automate a load of geospatial analysis processes for both specialists and non-specialists that can provide richer, accurate and trusted geospatial intelligence to military planners. My colleagues and I are Royal Engineers within the British Army. We specialise in delivering deployable geospatial intelligence to defence at both the strategic and the tactical level. And we do this so that we can enable our commanders to have mission success. We meet that requirement by doing 2 years worth of training to become intelligence analysts, and we are held at various stages of readiness, some of us at 1 hour's notice to move. We enable defence, including both our allies and our partners, with access to the full range of geospatial intelligence capabilities. This can include visualising the operating environment to ensure what we say, fight off the same map. And we deliver location-based services to support understanding and decision-making for other command and control applications. And perhaps more pertinent to today's presentation, I've skipped a couple of slides, is we exploit the where and the when to help planners understand the why and the what's going to happen next. Military formations will often have less than 4 hours to formulate what need to be pretty comprehensive plans with various courses of actions required to fall out of that. And the first question that's always asked is, what is the situation and how is that going to affect me? Considering the terrain and its implications on the decisions is a huge element of this, and initial considerations will be the weather, the meteorological effects on the battlefield, and the composition of the physical terrain, and whether that's going to create any vulnerable areas like dead ground or create any natural obstacles that will affect mobility, and also any key infrastructure that will affect manoeuvrability of our vehicles, but also the local population and its ability to function as normal. So the problem faced today is that in an ever more intense and perilous mission planning that's now always focused on peer adversaries with similar military capabilities, decision makers now require data-led insights in minutes rather than hours. Providing a detailed understanding of the terrain while simultaneously recommending locations to cross rivers, site artillery and land helicopters within a really short space of time can become very, very complicated very quickly.
So, what we did. We interviewed geospatial analysts that support the various formations across defence. We gathered their user stories of common products that they create in order to support military planning. We then prioritised those user stories based on the number of people that would benefit them or maximise benefit. And we then turned some of those into an automated workflow. In most circumstances, when we were devising these workflows, we did it initially in Model Builder. We then converted these into Python scripts so we could adjust them further. And then finally, we wrapped them up in a nice shiny geospatial toolbox so that we could, so our analysts could use them. So this was an iterative process. It wasn't a one and done. It was a case of fine-tuning those outputs for a wide range of defence. And this has culminated in the release of a dozen new tools across the last 2 years. So what we'll do now is we'll take you through a small selection of the tools, as well as a brief outline of their purpose and how they work.
Identifying vulnerable points or areas is usually a laborious task in which an analyst would manually assess the relief and infrastructure around a specific route, in identifying the most likely ground used by the enemy to gain an advantage with a minimized risk of compromise. These could be frequently used on long open stretches of road, dense built-up areas, or sections where routes lead to the canalization of troops. The VAVP tool greatly reduces the expenditure of effort and time to create the same output by automating the analysis using the same techniques an analyst would. Roads play a big part in the mobility of a convoy, hence the need for in-depth analysis to be conducted on an entire route. The tool calculates the angle of each turn or bend in a road and identifies vulnerable points where a convoy's speed may reduce drastically for a change of direction. Other road attributions, such as its width, can help the tool to determine whether a certain section should be traversed with caution. The tool uses the relief surrounding routes to depict areas of canalization, where troops may be forced through an area of disadvantage. Wood blocks of a certain size running along routes can provide the capability for an ambush. These are also considered and will be highlighted as a vulnerable area if the criteria is matched.
Sorry, I was a little bit keen to hand over to my colleague there, so what I'll do is I'll go back. Apologies for that. So what I'll do is I'll take you through the area, is the operational area evaluation tool. So this tool basically represents the lion's share of the work that we would do. No, it's that one. Sorry. We'll get there. We'll get there. There we go. Sorry, there's two screens on here. What's next and what I've got up there? I should probably look at that one, shouldn't I? So that's off-putting. So the operational area evaluation tool represents the lion's share of the work that we do at the start of any exercise or operation, and needs to be created and disseminated quickly. It gives a commander a good idea of the key information about the ground and how it can be used for both us and an adversary force. So how we do this is we normally create a base map and then we create a number of overlays, normally printed on clear film that we sit over the top. These would be themes that we're interested in, such as critical national infrastructure, the transportation network, or hydrological layout. So the production of this pack is very time-consuming, and it's a very repetitive task. So we automated it. The tool requires some input data, an extent, and a scale. That's it. So what we do is the first element of the tool will select a layout file suitable for that area at that scale. It will then dynamically set the symbology using layer X files, as well as dynamically adjusting the marginalia. Finally, the tool will then extract the layers as PDFs ready for printing. So doing this process manually can take several hours. However, using automation, we can get that down to normally within 15 minutes. So this frees up a lot of our time so we can then look at other things, ultimately keep giving us a competitive advantage over any adversaries. So the cross-country mobility tool. The cross-country mobility, or CCM, is a product that categorizes an area into 3 groups based on the ease of which it can be traversed. This takes into account factors such as slope, any obstacles, both constructed and natural, and the effects of weather, such as soil saturation. Again, traditionally this was done manually and is really quite labour-intensive. Although it was possible to tailor this to a particular vehicle, normally due to the time constraints, we used generic figures. So once again, we automated it. Whilst drawing in a wide number of inputs, sort of elevation, focusing on slope, hydrological features as they act as natural obstacles, land use to avoid wood blocks or urban areas, and finally soil and weather data to look at the load-bearing capacity of the ground. This then fused with vehicle-specific data in a lookup table allows us to combine the vehicle characteristics such as its load and the maximum slope that it can take. And then we can create a cost surface based on the trafficability of an area. This then allows potential mobility corridors to be deduced for both us and adversary forces, ultimately allowing us to outmaneuver them.
Crossing any obstacle is an enabling action that leaves a formation vulnerable to attack. So planning is a critical activity in the preparation. A wide wet gap is a significant obstacle that will usually form part of an enemy defensive line, heavily reinforced with artillery and mobile forces. Identifying suitable and safe crossing points in a timely fashion is essential. The aim of the wet gap crossing tool was to identify and display suitable crossing points along a stretch of river, taking into account the width of the river, the solidity of the river banks, and the difference in elevation on either side. With just a few simple inputs of a river polygon feature class, land cover, and elevation rasters, the tool returns a series of attributed and respectively colored segments based on the feasibility of a successful river crossing. The tool works by initially creating a center line through the polygon. Lines pertaining to the river widths are then created using transect lines. The segments are then created and the river line's attribution is joined to them, returning the areas with the corresponding width. To enable the tool to consider the difference in bank height, the elevation raster is spatially joined to the endpoints of the lines previously created. In doing so, we're left with the lines that span the whole width of the river, fully attributed with the widths and bank differences. To broaden the capability of this tool, an interactive filter with functionality provided by the update parameters function and the pandas Python library within the tool was used to enable the user to query a large international database of bridging assets and determine which specific asset the tool would base its analysis on.
So the Paratrooper drop zone tool. This tool is designed to support airborne operations and the selection of parachute drop zones. The tool is actually split into 3 sub-tools, so unfortunately isn't fully automated just yet. The first focus is on a multi-criteria analysis, basically establishing regions where forces cannot drop. This then is combined with the second element. So this is a polygon generation. So there's you take in the number of people that are dropping and at what altitude, and it'll give you an area that's suitable for that. You then take this polygon, and unfortunately at the moment have to manually place this on that multi-criteria analysis taken from the first element. That constitutes the second part of the tool. Finally, the tool then uses machine learning by comparing those potential drop zones that you've created with previously used military drop zones that we've got in the library. And then the final output of this will be a ranked list of those polygons in order of preference based on its characteristics. So this helps us whittle down the areas that will need further investigation from many to few.
Some military communications networks require line of sight to confirm a stable connection. If communications are not possible between 2 sites, a small formation will set up a radio rebroadcast station in between the original sites. This acts as a piggyback mast, allowing connection between all radios, much like a Wi-Fi extender you'd use at home. The purpose of the rebroadcast site selection tool is to identify tactically suitable rebroadcasting sites, considering factors such as concealment, defense, and technical suitability. Negative factors are also used within the tool's logic in order to avoid areas of absolute high or low ground. The process of the tool begins by checking if a rebro station is necessary. It does this by assessing the current line of sight between the 2 targets. If it is determined that it is necessary, the tool will create a viewshed raster from each mast at a given height within a diamond-shaped area between the original targets, returning the initial possible sites. These sites are then cross-referenced against an elevation raster in order to remove the areas that are located at the highest and lowest portions of the relief. Optional parameters are also available as inputs in order to alter the way the tool processes, providing the ability to change the sighting preference based on the user's requirements. For example, sighting the rebroadcast station only within woodblocks. The Formation Support Areas tool is used for modeling suitability of locations of sustainment assets that support operational headquarters. An army formation consists of a huge number of vehicles and personnel, and they require a large amount of equipment in order to support and sustain them. This is usually located at the rear of a battlefield, and its location is dictated by certain criteria, such as area size, somewhere with a solid foundation, and proximity to main supply routes. This tool converts a series of inputs into rasters before performing in-depth raster analysis in order to return the areas with suitable access to communications, infrastructure, and defense. You'll notice that the final output is a tessellation-based density model, and this is something that's being increasingly requested as an output format of geospatial intelligence, as some believe it's more aesthetically pleasing.
So, as you can see, we've built a suite of tools that can provide both geospatial subject matter experts and in the future non-spatial experts with a series of automated functions that can aid quicker decision making and, more importantly, in defence, information superiority. We believe the benefits of our work generally as follows. Automation has made our lives a lot easier. Once you automate a geoprocessing process, you don't have to put in as much effort remembering the proper sequence of the tools that you used and the kind of how they should be run. We've intentionally created our toolbox at the moment as a series of Python tools, as we're currently a little hamstrung by military disconnected ways of working. This is changing in the future. So because of that now we're trying to change too, we're trying to turn those Python tools into a series of widgets and geoprocessing services. And these are hopefully going to be hosted on a quite easy to use web app for our customers who will be the military planners and they're non-geospatial subject matter experts generally. We're also looking at creating bespoke ArcPro instances with the new Pro SDK, so we can create bespoke ArcPro instances that have just our tools along the ribbon rather than all the other stuff that might confuse non-geo SMEs. Automation has also made our work a lot faster. A computer can open up and execute tools in a sequence much faster than a human being can, as you'll often find with Model Builder. As mentioned, this has become increasingly important now in modern battlefields where we're planning against peer adversaries and people with similar capabilities to ourselves. And finally, we found our automation has made our work a lot more accurate. A lot of it's based on doctrine, and any time you perform a manual task on a computer, there's a chance for error, especially if you're under the time pressures that we often find ourselves. The chance for errors multiply with the number and complexity of steps in our analysis, and as well as the fatigue that can be incurred by just doing the same thing over and over again. In contrast, once our tasks have been automated now, the computer we feel can be trusted to run those same sequence of steps endlessly for a potential endless number of cycles. So this concludes our presentation for you this afternoon. On behalf of my colleagues, I'd like to thank you all for listening. We'll be around the conference centre for the rest of the afternoon. If you'd like to come and chat to us, we'll probably take our green pyjamas off and put something more suitable on. But no, thank you for your time and enjoy the rest of the afternoon.